Hi there, folks. Today we're looking at compound inequalities. And compound inequalities are really just two inequalities that we're kind of solving at the same time. And what we do is we separate those inequalities with either the word and or the word or. All right. An and inequality is when we want to graph the overlap, and the or inequality is when we want to graph the combination. And see the difference here, if you think about somebody using the word and or the word or, if I say that I'm going to bring pizza and donuts, you expect both of those things, so both conditions need to be met. All right. So the word and implies that each thing has to be happening. Okay. The word or implies that it's one or the other. If I said I'm going to bring pizza or donuts, if I only show up with pizza, you're going to be fine because I said I would bring one or the other. Okay. That's what the word or implies. And that's kind of what we're looking at when we talk about the inequalities. So the word and, the overlap, is basically what the two things have in common. It's this thing and this thing. So we're just looking for the points that count for both inequalities. All right. Whereas the or is, hey, I could have this thing or this thing, so I graph each of those completely, all right? And so here's what this looks like. We're going to start by looking at the graphs. And just like when we're graphing regular inequalities, we use the open dots and the closed dots and that kind of stuff. And so if I kind of think of this guy off to the side, let me bring it off to the side here. If we kind of think about where 7 and 3 are respectively, if I were to think about graphing x is less than or equal to 7, so less than or equal to 7 would be a closed dot and then everything to this side, all right? But greater than 3 would be an open dot and everything going this way, all right? And so if I kind of thought about grabbing one of those, like if I selected this guy and like moved it on top of this, where do they touch? In other words, where do they overlap? Where do I see both lines? And you see, I see both lines between 3 and 7. And so when I actually graph this thing and inequality, if I'm only graphing where they overlap, I only graph where those two things would touch if I put them on top of each other. Basically, my graph is going to look like this. I've got the 3 down here, the 7 up here. I'm going to have an open dot at the 3, a closed dot at the 7, and I'm going to shade everything in between. See, because if I said something like, let me choose a number in between there, like 4. Is 4 less than or equal to 7 and greater than 3? The answer would be yes. The 4 is less than or equal to 7. The 4 is also greater than the 3. But if I did something like a 2, it would say 2 is less than or equal to 7 and 2 is greater than 3. And while 2 is less than or equal to 7, it's not greater than 3, so it only meets one of those conditions. It only works for one inequality. And so when I look at this graph, when I look at shading in between there, those are all the values that work for both inequalities. And that's it. Okay, so this is what our graph is going to look like. And if you need to graph both of these and then graph it separately for the overlap, that's fine. The or is really the awesome one here. So the or is great because I don't have to worry about overlap and that kind of thing. So I've got -3 and I've got +2. So if I graphed the less than or equal to -3, that would be a closed dot and shaded this way. Greater than 2 would be an open dot and shaded this way. And that's it. I literally graph each of them because I don't need them to overlap. I don't need both of these conditions to be met. I need one or the other. Like if I used a -4, is -4 less than or equal to -3 or greater than 2? Well, yeah, because it's less than or equal to -3. It doesn't matter that it's not greater than 2. It's one or the other. And likewise, if I went to the other side and picked something like a 3, is 3 less than or equal to -3? Well, no. But it's or is 3 greater than 2? Yes. Okay, so 3 is greater than 2, so one of those works. Okay, and that's the idea behind the or. We keep both of them completely because we just need one of them to work. Where with the and, we can only use the parts that work for both. Okay? You might also see and inequalities written this way. Keep in mind that this means two things. This means I have x is greater than -4. Notice I'm reading a little bit backwards if I read from the x. And then x is less than or equal to 1. And that's an and inequality, so that's an and for those two. All right? It means the same thing. Most of the time, this is how we write those inequalities, though. Okay? And what's nice about this, if you think about the way this is written, we've got x in between a -4 and a +1. And just like my graph up top, I shaded between 3 and 7. Well, here, x is literally between a -4 and a +1. So I'm going to shade everything in between the -4 and the +1. And I use an open dot at -4 because there's no equal to condition here, but I use a closed dot up here at 1. And so when they're written in this format, they're actually easier to graph than when we have the word and in between, because the x is literally in between those values, okay? If I look at the next one, same kind of thing. So let me get my graph going. It's an or inequality this time, so it can be one or the other. So I graph each of them completely, and I did that completely backwards. -6 is smaller than a -1, so -6 goes down here, -1 goes up here. So then greater than or equal to the -1, that's a closed dot and everything this way. Less than a -6 is an open dot and this way, and that's it. I don't have to worry about overlap or being in between two values. I just graph each piece separately, okay? If I look at something like this guy, we can see that x is literally between -2 and +5. So when I graph it, I literally draw x between -2 and +5. And notice it's a closed dot for each of them because the equal to conditions, and that's it. Okay, so that's how we graph and inequalities. It's the overlap, all right? And then this one, the or inequality here. So let's see, it says less than a -2, so that's an open dot and shaded this way. Greater than 3 is an open dot and shaded this way. I just graph each of them completely, okay? So again, with the and, we're only graphing where they crisscross. With the or, we're graphing everything. So solving compound inequalities, since a compound inequality is just two inequalities, we just have to solve two inequalities, all right? And so the idea here is there's a couple ways we can do this, especially with the and, all right? The ors are pretty straightforward, all right? The and, you could split this up and say, hey, I have one inequality that says -4 is less than 3x minus 1. And I would also have the inequality 3x minus 1 is less than or equal to a 5. That's literally what this thing means. I just write it so this way that we have this written is kind of shorthand for this thing, but I could split it up. So it's two inequalities. I just solve each of these. So this first one, to solve, I work backwards sort of operations, undo them as I go. So I'm going to add the 1 to each side, because that's how I get rid of subtracting a 1. And now to undo multiplying by a 3, I'm going to divide by a 3. So here I get a -1. I still have the less than symbol, and it's an x. And I'm not going to bother rewriting that. I'm going to leave it the way it is. Over here, I'm going to go ahead and add the 1 to each side. That's how I undo subtracting 1. Then I'm going to undo multiplying by the 3 by dividing by 3. And I don't have to flip the inequality symbol. Remember, you only flip the inequality symbol if you multiply or divide by a negative. But then at the end, I would have the word and in between here. Well, look at the way this is written. I can slap this thing back together. It's a -1 less than x less than or equal to 2. And I can rewrite it back in that same format that I started with. Okay. Now, with that said, here's the shortcut for doing this. I'm going to do this one again. Don't be alarmed. I'm erasing everything. Oh, boy. But here's the thing, when you think about solving each of those equations, or each of those inequalities, they both had the same steps. Each of them, I added a 1 to each side, and then I divided each side by 3. So I'm just going to do it all in one shot. Watch this. I'm going to add 1 to this guy to get rid of the -1, but I have to do it over here and over here. I just have to add it to all 3 sides now. And what happens is I'm going to solve the same two inequalities I solved before, but I'm going to do it simultaneously. And now to undo multiplying by a 3, I divide by a 3. And keep in mind, I'm undoing what's happening to x because that's the thing I'm trying to solve for. So now I get a -1, here I get an x, and here I get a 2. And notice I have the same answer, but it caused me to do a little bit less work, okay? Either way is acceptable. Just make sure you rewrite it as one string of characters when you're done, okay? With the or inequalities are pretty straightforward. We just solve each of these separately. So like this one, I ignore that second inequality, ignore everything after the or, and I just see x plus 2 is less than or equal to the -3. Well, to undo adding a 2, I'm going to subtract a 2. So I end up with x is less than or equal to a negative 5. And now I say, okay, that one's done. Let me go to the next one. The next one I have multiplying by 5. To undo that, I divide each side by 5. And notice I did not multiply or divide by a negative, so no need to flip the inequality symbol. Stays the same. There's a 3. And then to finish this thing off, I just slap the word or in between. Okay. The last thing I would probably do on each of these, however, is I would draw a quick sketch of the graph. Okay. And again, the only reason we're drawing the quick sketch of the graph is to make sure that this thing makes sense. We didn't have any so far that don't make sense, but if I had something like this, it would be between -1 and 2, and an open dot here and a closed dot here. We run into issues if I had something that looked like this. Imagine if I had 2 less than x less than or equal to a -1. See, that's a problem, because how can x be bigger than 2 but less than -1? Okay, so just watch out for those values in terms of least to greatest. If it gives you impossible situations, well, the graph will help us identify that. And then here, let's draw a quick sketch of the graph. And again, if for no other reason, just to practice graphing a little bit. So here, less than or equal to the 5. Here, greater than the 3. Okay. If I look at this guy, again, let's use that shortcut that we were just talking about and say, hey, instead of splitting this up, I'm just looking at what's happening to x. Right now I have 1/2 times x and then minus a 3. So I undo the -3 by adding 3 to each side. And again, it's basically like I have 3 sides, so I do it to all 3 sides. So here that gives me an 8. Got that 1/2. Remember, a 1/2 is the same thing as divided by 2. So to undo that, I'm going to multiply by 2. And I have to do that to all 3 sides. So I get 16 less than x less than or equal to 20. Okay? And we're going to skip the graph on this one. You'll have plenty of time to practice graphing. But if I graphed this, I would just be between 16 and 20 with an open dot at 16 and a closed dot at 20. Okay? If I look at this guy, again, solve each of them separately. Here, I'm going to add the 4 to each side. So that gives me an x is greater than or equal to a 10. Over here, to solve this one, I'm going to divide each side by a -2. So I end up with x is less than a -4. We had to flip the inequality sign because we divided by a negative. And now I slap that or in between. And that's it. Done and done. All right. Once again, if I graphed it, I would just graph each of those inequalities separately, but on the same number line. If I look at this one, so again, I'm going to use that shortcut and say, all right, what's happening to x? X is being multiplied by -2, and we're adding a 3. So I undo addition first by subtracting. So I undo addition by subtracting 3 from each side. And now I undo multiplication by dividing. And what happens here is I just divided by a negative, so I have to flip all those inequality signs. So here I get a 3. I flip this, and it looks like this. I flip this guy, and it looks like this. And if you notice, this one's not written the way all the rest of them have been written. The rest of them were written from least to greatest, and they all used less than symbols. I should do the same thing here. So I should write the -1 first, and make sure that, and then the x, and then the 3. And make sure the alligator's eating the same stuff. Like here, the alligator's supposed to be eating the x. Okay, but between the x and the 3, the alligator's supposed to be eating the 3. So just make sure you keep it in the same kind of order, all right? We want to go least to greatest, but make sure those inequality symbols are facing the right way, okay? We always want to go from least to greatest. And see, the nice thing about doing that is it's really easy to see, okay, now x is bigger than the -1, but smaller than the 3. It's in between the -1 and the 3, okay? If I look at the next one, we're going to subtract that 6 from each side. And now I'm going to divide each side by the 2. And don't be fooled here. There's no need to flip the inequality sign. Even though I get a negative answer, I didn't divide by a negative, okay? The negative was a result of what was there. Only if you multiply or divide by a negative do you flip the inequality sign. If I look at the next one, oh boy, I see a lot of fractions floating around. And maybe you're thinking, hey, let's subtract that 3/4 from each side. But remember, Mr. Jansen told you a pretty sweet trick. Every time you see fractions, Those are basically saying divided by 4, divided by 4. Let's get rid of that divided by 4, and you can get rid of the dividing by 4 by multiplying by 4. We multiply through by the common denominator. And so here, when we distribute this thing, that just says 4 times 1/4. That's like saying 4 divided by 4, which is 1. Right here, that's like 4 times 3 divided by 4. Well, 4 divided by 4 is a 1, so I'm just left with the 3. Okay? And then over here, looks like I've got an 8. Okay? And now let's subtract that 3 from each side. Again, you could have subtracted the 3/4, but you can always get rid of fractions by multiplying through by the common denominator. Let me write this guy a little bit lower. And then I slap my or in between, and that's it, okay? So that's all there is to it in terms of solving compound inequalities. It's just two separate inequalities that we solve the same way we always solve inequalities, okay? Remember that you still have to flip that inequality sign if you multiply or divide by a negative. And then we have that special notation with the and inequalities where it's kind of written all as one thing. Well, instead of splitting it up and solving two inequalities, we solve them simultaneously. So think about what you need to do to solve for x and do that to all three sides, okay? There's a few special cases that we could look at, but we're not going to worry about those today, okay?